and this. All right. So, guys, here we go. As I shared with you on what's today? Monday. As I shared with you on Monday, guys, we did something kind of weird on Monday. We started a unit with a lab. And guys, typically we do not start units with labs because we use labs as reinforcing activities and not introductory activities. So why did we start with the lab? And guys, honestly, the reason that we started with the lab is because if we were to just dive in right here the very first day of this unit, so much of this would be so new that it just creates more confusion than it does clarity. So guys, remember on Monday when we introduced the lab, there was a little bit of teaching, right? And along the way I said, guys, don't take notes because this stuff is so important that we're going to come back and talk about it again on Wednesday. So guys, that's what we're going to do today. So as we go through this material today, you should have that experience of going, I've heard of this before. Not I understood it, but at least I've heard of this before. And guys, what we're going to do is we're going to take some of these ideas that you were introduced to in lab and we're going to solidify them. So what are the things that you should at least be aware of right now? So guys, let me give you those things. Don't write any of this down, but I just want to lay these at your feet so that we can all agree that at least we've talked about these things. So guys, in no particular order, last period, guys, we introduced these interesting ideas. First of all, acids have lots of hydrogen ion. Can you all get behind that? And guys, how do we measure the amount of hydrogen ion? pH, and we'll talk more in a second. So if acids have a lot of hydrogen ion, what do bases have a lot of? OH, hydroxide ion. And guys, we're going to talk more about that today, but at least fundamentally, we understand that acids have got a lot of that and bases have got a lot of that. So what else did we talk about? Well, guys, we talked about water having equal amounts of both of these. It's water, right? HOH is H2O, and water is perfectly an acid and perfectly a base because it perfectly contains both. You guys okay with thought number 3? Okay, thought number 4 then is this. We've got this thing called the pH scale. We use the pH scale to measure the strengths of acids and bases, and we also learned that this pH scale is a logarithmic scale, and answering this question in the conclusions for the lab, you guys hopefully communicated the idea that a logarithmic scale is a scale that goes by powers of 10, and that's important because when the pH changes a little bit, the concentration of the acid changes a lot because it moves by powers of 10. Can I get an amen? You guys okay? We doing all right? All of this, can we agree on this? Go ahead.
So, just kind of like the lab, we made the pH scale using
the droppers?
Yeah.
Yeah.
It seemed like number 1.
Yeah.
We say that like number 1 pH acid is really strong, but we only use 1 molar hydrochloric acid.
Yeah.
So is that like the actual scale on there?
No. Here, so I'm going to just draw my finger. But, oh gosh, come on. Maybe, oh, my board's turned off. Never mind. I'm not going to do anything with my finger, and now I'll get a pen. So guys, the question on the table is, wait, we used a 1 molar acid, and that's strong, but not that strong. So what is actually the pH scale? And so the answer is this. We said 7 is in the middle, 14 is the high end, and 1 is the low end, right? And that's what we built in lab. But if you remember the way we built this in lab, and we're going to talk about this today, the acid that we had that was that had a pH of 1, its molarity was actually 0.1 molar. Guys, check this out. This is going to be a big idea today, but we may as well talk about it now. So this is, just watch, because we're going to come back to this. And if you see it now, it might make it easier later. So here's what we know. 0.1 molar acid has a pH of 1. Ready for the connection? Guys, how do we write 0.1 in scientific notation? 10 to the negative what? First. And guys, that's where the pH comes from. So the idea is the pH is the negative exponent of the molarity. So if we've got a 0.1 molar acid, that has a pH of 1. But now this gets weird, because remember where we started. We started with 1 molar acid, right? So what is the pH of 1 molar acid? Well, how do you write 1 in scientific notation? 10 to the what? 10 to the 0. So that would actually have a pH of 0. But we also have 10 molar acid over in our stockroom. So how do we write 10 in scientific notation? Well, that would be 10 to the first. The pH of that is -1. So the pH scale, let me see if I can do this well. Guys, the pH scale actually does not go from 1 to 14. The pH scale actually goes from about -1.3 up to about 16.2. That's actually, so why do we say it goes 1 to 14? Because in biology, in the natural world, that's true. But in a chemistry lab, we can go way outside of 1 to 14. They are, yeah. So this is actually 18 molar sulfuric acid. If you take the inverse log of 18, it's 1.26 actually. And then this up here, this stuff terrifies me, is 20 molar sodium hydroxide. We actually use that in AP lab, and it scares the crap out of me. I hate that stuff. Yeah, so these are sort of the high and low end, are really concentrated sodium hydroxide and saturated sulfuric acid. So how about that for an interesting conversation? So guys, back to what we were doing. You guys all good with these ideas? Any concerns, things you want to talk about, or based on these ideas, can we go forward? Y'all okay? All right. So guys, if we can all agree on this stuff, what I'd like to do then, and you don't need to write this down either, I'd like guys for us to talk about what are we going to do today. So guys, today what we're going to do is we're going to answer some questions. Question number 1 is this: what is an acid? What is a base? But you already kind of know the answer, right? What is an acid? What's it do? You told me you agreed on the previous page. What does an acid do? Gives away hydrogen ion. What does a base do? Gives away hydroxide ion. But guys, what you're going to find out is it's not quite that simple. And there's a lot of intelligent people that have thought about acids and bases. It turns out that there are 3 definitions for acids and bases. The one you don't need to know. It's actually the Lewis definition, the same guy that came up with Lewis dot structures. But guys, there's 2 other definitions that you need to know, and we'll talk in a minute. Then guys, after that, we're going to talk about this. What do acids and bases do when they react together? A follow-up question to that, number 3, is what do they form when they react together? And then guys, finally, question number 4 that we're going to answer today is why do stronger acids have lower pHs? Which is what we just talked about up here on the screen. Guys, the idea is that the lower the pH, the stronger the acid, and we're going to talk in a minute about why. So guys, this is our laundry list for today. What are acids and bases? How do they react? What do they form? And what's up with the pH scale? You guys ready to go? Okay, one at a time. So we are going to start here. So guys, when we talk about acids and bases, and you don't need to write this down, guys, when we talk about acids and bases, we've already established that acids give away hydrogens and bases give away hydroxides. So now what I want to do is I want to ask you just to see where you're at with this. So guys, let's talk about acids first. What are substances that you know to be acidic? What are acids? Give me examples of acids. What vinegar is an acid? What else? Say it again. Did you guys know that? Lemon juice is an acid. But did you also know that orange juice and grapefruit juice and all, and do you know that they all contain the same acid? Citric acid. Good for you. And I'm actually going to put its formula on the board. Nice job, Fred. What else, you guys? What are other things that are acids? Say it again. Oh my. Yeah, did you hear it? DNA. That's RNA. No, so deoxyribonucleic Acid. That's what the A in DNA and RNA stands for. Those things are also acids. Other things that you know to be acids. Yep. Say it again. Amino acids that make up what? What do our bodies do with amino acids? Turn them into what? Proteins. You string together these amino acids and they all turn into proteins. Guys, what are other things? You guys are doing really well. What are other things that you know to be acids? Say it again. So let's talk about that. Guys, you all understand that your spit is acidic, right? Do you know why your spit is acidic? Where does the acid come from? Your gut. It's actually, you guys understand that, right? That your gut, your stomach is just a big bag of acid. Do you know what acid is in there? Well, yes, stomach acid, but what acid? That was wildly obvious. But guys, what acid is stomach acid? Do you guys not know? It's actually hydrochloric acid. So guys, your body actually generates hydrochloric acid and dumps it into your stomach. Now here's an interesting question, because guys, your stomach acid is actually more concentrated than the acid that we just used in lab. In the previous lab. Remember, we used HCl, right? Guys, the same HCl that we had in a squirt bottle is the HCl that's inside your stomach. And every time we do a lab, I tell you, don't get this acid on you because it will burn. But now you know you've got a bag of that acid sitting right there in your gut. So guys, why are you not continually getting acid burns if you've got a bag of acid that we call your stomach sitting right here? Your stomach is lined with what? Mucus. It's actually boogers. Do you guys know this? Your stomach is actually lined with the same sort of mucus that your nose makes. But guys, I don't know if you understand this. So the mucus protects your stomach, which is flesh and muscle. Guys, it protects your stomach from the acid. But what happens if the mucus lining in your stomach gets holes in it? Well, yeah, then you start to digest your own stomach, and that's called an ulcer. Say it again.
That's why when you're hungry,
yeah?
you don't have food in your stomach, and your stomach's telling you, hey, you need something down here, otherwise we'll...
Because there's too much acid, absolutely, yeah. So guys, you guys did amazingly well, but maybe let's try this. So guys, these are things that I would like us to agree are all acidic. So interestingly, none of you said battery acid. So guys, do you know the acid that is in the batteries in our cars? Oh yeah, it's horrible, horrible stuff. Guys, it's actually sulfuric acid, which is H2SO4. Then guys, we already talked about this one, stomach acid, which is HCl. Then interestingly, Freddie mentioned, not this one, but you guys know about this one, right? Yeah, lactic acid, the stuff that builds up in your muscles. This girl's crazy. She's so fast. But anyway, so her name's Lizzie Digan. But so guys, you whether you're a cyclist or a runner, you understand. And do you guys know how this works? The buildup of lactic acid. So guys, you have this thing that's called your lactate threshold. You've probably heard about the difference between aerobic and anaerobic activity. So guys, aerobic activity is actually activity where you can breathe fast enough for your body to get rid of the waste that comes from metabolism, and your body can get rid of that, and that is what is called aerobic activity. Your body can keep up, you can get enough oxygen to your muscles, and everything works fine. Well, guys, then you have this thing that's called your aerobic threshold, which is also what's called your lactate threshold. And what happens is when you get to this point, you can no longer breathe and your heart can no longer beat fast enough to get the byproducts of respiration out of your muscles, and your muscles actually switch to another metabolic pathway, and the result of that metabolic pathway is actually lactic acid. And that lactic acid builds up in your muscles and your body can't clear it, and that's when your muscles start to burn. And if you're an athlete, you've had that experience of hitting your lactate threshold, because when you hit your lactate threshold, you can't breathe, you can't talk. Have you ever had that experience where you're running or riding and you can no longer carry on a conversation, and it's your body going, I've got to focus on breathing and I can't do anything else. And at that moment, your muscles start to burn, and you know that you're now creating lactic acid, and as it builds up in your muscles, it really starts to burn. And so what you're actually generating is lactic acid. The formula for lactic acid, guys, is actually really simple. It's C3H6O3. Yeah. That's why it burns. The idea is it's literally lactic acid. And understand, it's not strong enough that it like eats your flesh, but it is strong enough that it burns. And that's why it burns, because it's an acid and it's literally creating that burning sensation in your muscles. Yeah, isn't that interesting? And then, guys, finally here, and this is the one that Freddie came up with, lemon juice, which its chemical formula is C6H8O7. And guys, all of these are acids. But here's the thing that's interesting. If they're all acids, what do they all contain? Do you see it? Hydrogen, 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 hydrogen. Guys, they all contain hydrogen. Does that make sense? Okay. So now, guys, let's talk about bases. You ready to have a much shorter conversation? Tell me all the things that you know are bases. Baking soda, right. What else what'd you use in lab? Sodium hydroxide. What else you got? Not much, right? Guys, isn't that interesting that we could have been here for an hour talking about all the things that you know are acidic, and you guys came up with amazing examples like DNA and RNA and the building blocks of proteins. And then when we talk about bases, you can hear the crickets chirp, right? So, guys, we don't talk as much about bases, but you got to understand they're every bit as important as acids, and we're going to talk about them today. So let me just give you some examples. So, guys, oven cleaner is a base. Did you guys know that? Oven cleaner is not an acid, it's a base. So if you've ever bought a can of Easy Off oven cleaner and sprayed that hideous stuff inside your oven, that is actually concentrated sodium hydroxide, the same stuff we used in lab last time. It's just so concentrated that it just rips the food yuck out of your oven. So guys, another thing that is a base is actually Rolaids and other antacids. Doesn't that make sense? So Tyler was talking about this idea that if you've got no food in your stomach, your body's going, hey, yo, give me food. But guys, sometimes you know that burning sensation you get in your stomach? Well, guys, the problem is that you've got too much acid in your stomach. So what do? You take Rolaids or Tums or whatever. And guys, this is an antacid. It's an opposite of an acid. It's a base. And that base goes down into your stomach and it neutralizes the acid. So guys, what is the base in Rolaids and Tums? It's actually aluminum hydroxide. They actually, a few years ago, thought about changing the base in Rolaids because there was some evidence that aluminum caused Alzheimer's disease. And so they were actually thinking about removing the aluminum from these things. They were even thinking about removing like aluminum pans, because there was concern that cooking in an aluminum skillet would actually put aluminum into your food, and there was some thought that it might cause Alzheimer's. Interestingly, there's also a lot of aluminum in deodorant. And so they were thinking that they were going to have to pull aluminum out of deodorant as well because of some loose connections to Alzheimer's. Turns out it's been disproven and everything's fine. But guys, aluminum hydroxide is also a base. So let me give you two more. Do you guys know this one? Ammonia is a base. Remember the ammonia that we used in lab and I told you not to huff it, but you went like this and you're like, oh boy, that's strong. But guys, even the ammonia that you use at home as a cleaner, that is also a base, and its chemical formula is NH3. And then guys, you may know this one as I turn on the lights. Did you know that chalk is a base? Yeah, chalk, sidewalk chalk, or the chalk that we used to write on chalkboards with is a base. It's actually calcium carbonate. So guys, let's do this again. We said that these are acids, and what do all acids contain? Hydrogen, and we see it. And now we've come over here, and we've talked about the bases, and what do all bases contain? Hydroxide, and we come along, and we've got a problem. What's the problem? Yeah, guys, here's our hydroxide, and here's our hydroxide, but now we don't have any hydroxide. So guys, this is why we need two definitions for bases. Guys, acids always contain hydrogen. But this is interesting. Bases do not have to contain hydroxide, and we're going to talk more about this in a minute. But guys, a lot of bases do contain hydroxide. But you're going to find out in a minute, some bases do not contain hydroxide. Baking soda is another example. There's no hydroxide in baking soda, and yet it is a base. So this is why we need two definitions, because one definition simply talks about hydroxide. The other definition explains why these are bases. Do you see where we're headed? So here we go. So guys, let's talk about these definitions, and this is where you're going to start taking notes. So guys, definition number one, and these definitions are named after the chemists that proposed them. Definition number one is called the Arrhenius definition of acids and bases. This, I think, was proposed in like the mid-1800s, 1850, 1860, something like that. Guys, back in these days, you want to know how they tested to see if something was an acid or a base? They tasted it. So think about it. What does lemon juice taste like? Yeah, all acids taste sour. So literally, if they wanted to test and see if something was an acid, they'd put it on their tongue. And if it tasted sour, it was an acid. Imagine doing that with battery acid, right? Yeah, but guys, literally, that was their acid test. And then their base test was actually not based on taste. It was based on feel, because bases actually feel soapy. Guys, all soaps are bases. And it turns out that bases feel soapy, and so to test for bases, they would actually rub them between their fingers to see if they felt slick or soapy. So, given where this is coming from, it's kind of crazy science. Yeah? Yeah, right. So if you put it on your tongue and go, hey, that's not sour, then you know it's not an acid. And actually, bases do have a distinct taste as well. They're bitter. Bases taste bitter, but they would also feel them to see if they felt soapy. So guys, Arrhenius, 1850s, eating stuff, not a good idea. Here's what he said. Acids release hydrogen ions. Sounds familiar, right? We already agreed that we know that this is true. And then guys, definition of a base. You want to guess what it is? What do bases release? OH. See guys, this is the stuff that we've been talking about. So last time in lab, when I taught you about acids releasing hydrogen ion and bases releasing hydroxide ion, we were talking about the Arrhenius definition for an acid and base. So Arrhenius's definition is the definition we already know. But guys, we've already taken this even a step further. So the next thing we're going to do is we're going to talk about what happens when they react together. So guys, you already know the answer to this. If you take an H from a hydrogen and you take an OH from a base, and if you put them together, what do you get? Water, right? Guys, that's the general reaction. It goes like this. You take an acid and you take a base and you react them together, you get water. But guys, look at the other thing you get. Salt. Isn't that interesting? And remember, not sodium chloride, because you learned what is a salt? A positive and negative ion bonded together. Reviewing for the final that you have at the end of May. No, so this is a part of that definition. So in the Arrhenius definition, acids give away hydrogens, bases give away OHs, and they form salt and water. So guys, let's take a look at this. Let me show you an example, and Nate, I think this will come together. So guys, let's look at an example of an acid-base reaction. So let's do this. Let's take the acid that's in your stomach and then let's neutralize it with the base that is in the Rolaids. So you go home tonight, your stomach starts to hurt, you grab a Rolaids, you toss it back, you chew it up, and you swallow that thing, and it goes down in your stomach. And what chemistry happens in your stomach when the Rolaids gets mixed up with the HCl? Well, guys, let's do this. So, oh boy, actually, hold on. I forgot I didn't animate this. So, guys, what is the chemistry that's going to take place inside of there? Well, guys, let's do this together. Write it down with me. So, stomach acid is HCl. Rolaids is aluminum hydroxide. Oh, that's Al. Or So what are we going to form? Well, guys, we know one of our products is going to be water. How does that happen? Well, the H hooks up with the OH. Double displacement reaction. Interestingly, these are all double displacement reactions. So guys, the H hooks up with the OH. So what's going to happen to the aluminum and the chlorine? Well, they're going to get together, but guys, aluminum is +3, chlorine's -1, so our product is going to be AlCl3, and then in order to balance this, we need a 3, and we need a 3, and that now balances. So guys, this is the reaction that takes place in your stomach when you eat a Rolaids. The aluminum hydroxide goes down into your gut, it reacts with the acid, and you make water, and you make aluminum chloride salt. Aluminum chloride salt is harmless, water is pH 7, and there you go. You are now neutralizing the acid in your stomach, and it doesn't burn anymore. You get the idea? We okay? All right. So guys, let's go back here then. So here's what we now can understand. We understand that things like HCl are an acid. We understand things like aluminum hydroxide are bases. And we now understand the chemistry that they do. We now ready to talk about our other bases? Because guys, now we've got to explain this. How is it that NH3, how is it that CaCO3, how can those things be bases if they don't contain hydroxide? Well, guys, in order to answer that, we need another definition for acids and bases. This comes compliments of two researchers who actually didn't work together. They weren't lab partners. But they came up with these ideas at the same time, so they both got credit. Their names are Bronsted and Lowry. And I'd like to point out that I spent the time to find the O in Bronsted with a little line through it. It was hard, but I found it. So guys, here's what Bronsted and Lowry said. Ready? First, the definition of an acid. Bronsted and Lowry said this: acids are proton donors. Do you get it? One of you might figure this out. Guys, do this with me. We now understand that Bronsted and Lowry said this: acids donate protons. Guys, go up and look at the Arrhenius definition. What did Arrhenius say acids do? Donate what? Hydrogen ions. Did any of you see it? They're the same. Guys, let me explain to you. And if you don't understand that they're the same, you want to write this down with me. So guys, again, reviewing for the final. Hydrogen is element number 1 with a mass of 1. So guys, what does it mean that hydrogen is element number 1? What is in its nucleus? 1 proton. Now, what does it mean that it has a mass of 1? How many neutrons does it have? None, right? Because the protons plus the neutrons equal the mass. And so guys, a hydrogen atom actually looks like this. And if you don't understand this, you may want to write this down. So guys, this is a hydrogen atom. 1 proton, no neutrons, 1 electron. And now guys, here's the trick. Now we need to make this a hydrogen ion with a +1 charge. So again, reviewing a little bit for the final, what do we have to do to give a hydrogen atom a +1 charge? What do we do? Now do you get it? So guys, this is now a hydrogen ion. That's the Arrhenius definition, right? Arrhenius said acids give away hydrogen ions. So in order to make hydrogen into an ion, we take away the electron. But when we take away the electron, what's left? A proton. And that's the Bronsted Lowry definition. So guys, I can't do this in my slides, but you may want to do this in your notes. So where you wrote down the Arrhenius definition and it says hydrogen ion, and where you wrote down the Bronsted Lowry definition, wherever that went, and it says proton donor, you may want to draw a little line between those and write the same, because they are the same. Guys, hydrogen ions are protons, and consequently, these things are the same. So guys, if you chose not to draw the line, you could at least write down what I threw up on the board. Hydrogen ions are protons, and as a result, they're the same. The definitions are the same. But we would expect that. We're going to find the difference when it comes to bases. So guys, let's define bases. Here's the difference. Guys, in the Bronsted Lowry way of thinking, bases do not have to contain hydroxide. Bases simply need to be able to accept protons, which, as we now know, are the same as hydrogen ions. So guys, this becomes a really big idea, because now that we have a new way of thinking about bases, the reactions look totally different, because now an acid-base reaction involves an acid giving away a proton and a base accepting that proton. And guys, when that happens, the general reaction looks totally different. So guys, write this down with me. And then let me just tell you right now, this is one of the big nuggets for today. Guys, what I'm about to show you is something that you've got to be able to understand and do. And guys, we're going to do it today, but when you come back for AP chemistry next year, we are going to spend weeks talking about these reactions. But let me introduce it to you now. So guys, the general reaction goes like this. An acid reacts with a base, and it forms, here's a big word, a conjugate acid and a conjugate base. So, guys, I took Spanish in high school. Wasn't a great experience. Do they still talk about shoe verbs in Spanish? I love it. It never made sense to me, but that's okay. So guys, one of the few things that I do remember from my Spanish class, besides the two words siesta and fiesta, was that, guys, we spent a lot of time conjugating verbs. Yes? So, and I know you do this in French. I don't know if you do this in other language classes. But guys, this is where I first became aware of this word conjugate, because they were teaching us the IR verbs and the ER verbs and voy, vas, va, vamos, I don't know. But guys, bottom line is I learned about the word conjugate. And every time they told me to conjugate a verb, what I was doing was I was using rules to turn a verb into a new form of the word. Do you know what I'm saying? Guys, so the word conjugate means to turn into something else. So in the context of chemical reactions, what we're doing is we're taking an acid and a base and we are turning them into a new acid and a new base. So when we say conjugate acid, we mean a new acid. And when we say conjugate base, we mean a new base. It's new acids and bases formed by the original acids and bases. So guys, this is very important. In this class, all you've got to be able to do is identify the conjugates, and I'll show you how in a minute. In AP, we spend weeks talking about the chemistry of conjugates. We're not going to do that in here. In here, all you got to be able to do is identify them. So guys, let me define them for you. What is a conjugate acid? A conjugate acid is the thing that is formed when the base gains a proton. So bottom line is this: the base becomes the conjugate acid, and when it does, its charge goes up by 1. And I know that went really fast, but I'm pausing to let you catch up. You guys, I know you're sitting here going, oh my gosh, I know this is important and I'm not sure what he's talking about. You're okay. Just write this stuff down. I want you to have the experience of letting this flow from your eyes to your brain to your hand. And then we're going to talk about what you've got to be able to do with this. This is a do and not a know, but you've got to know before you can do. So I'll talk you through this. For now, you just need to at least have experienced the definitions. So a conjugate acid is formed when the base gains a proton. So basically, the base becomes the conjugate acid, and when that happens, the charge goes up by 1. Similarly, the conjugate base is the thing that is formed when the acid loses or releases a proton. So fundamentally, the acid becomes the conjugate base, and when that happens, the charge goes down by 1. And again, guys, I know your heads are swimming. You're going, what does this mean? I'm going to show you examples, and then you're going to go, okay, I'm all right. I promise. Unless you're still confused, and then never mind. So guys, when you're done writing this down, we're going to switch to a new slide. And guys, what's going to happen is I'm going to show you some examples of what you've got to be able to do with this. I'm going to ask you to not write them down. I simply want you to see the process. Along the way, there's 2 terms that we're going to define. And then guys, after we're done with that, we're going to switch to another clean slide, and I'll give you some more examples to look at. And then if you choose to write those down, you can. But guys, my experience has been the best way to learn this is to just see the application, and then we'll work on some others after that. So guys, I hope you appreciate that this is one of the biggies. You have got to be able to do what we're about to do on the screen. You've got to be able to identify acids and bases and conjugates. So here's the way this is going to work. I will give you a balanced equation. Again, you're not writing this down. Because I will give you a balanced equation, and what you'll be asked to do is identify the acid and the base and the conjugates. Now guys, this is all Bronsted Lowry, so think with me. First of all, Bronsted Lowry, what does an acid do? Look at your definition. What does it do? Gives away a proton. What does a base do? Takes in the proton. So guys, to figure out which one is the acid and which one is the base, you've got to ask yourself, which one of these is giving away a hydrogen, a proton? Which one of these is giving away a hydrogen? Which one's gaining the hydrogen? So how do you do that? By comparison. So guys, check this out. Here's how you do this. I'm going to shut off my board so I can touch it. So guys, here we have H2SO4. What looks like H2SO4 on the other side? The first one or the second one? Second one, right? So now you compare. This is H2SO4. This is HSO4. So guys, what did H2SO4 do? Did it give away a hydrogen or did it take in a hydrogen? It gave away a hydrogen because here it's H2 and here it's just H, so that gave away a hydrogen. And if you give away a hydrogen, what does that make H2SO4? An acid. So guys, you just identified the acid. Guess what, guys? Once you identify one of these, everything else becomes easy. Check this out. If this is an acid, what does that have to be? The base, right? So let's make sure that's true. Here we have H2O, there we have H3O. So guys, what did the water do? Took in a hydrogen. Doesn't that make it a base? Now guys, watch this. Now you've got to find the conjugates. This is the easiest way to do it. Go to the acid, take away a hydrogen. I can't really do that very well. Take away a hydrogen from the acid. When you do, the thing that you just formed is the conjugate other guy. So the acid becomes the conjugate base. So the acid becomes the conjugate base, and then the other guy is then the conjugate acid. You see the flow? This is important. You've got to be able to do this. Let's do another example. So let's do this again. Again, you're not writing this down, but here's the flow to this, guys. CH3COOH, water, H3O, CH3COO minus. So you go to the first thing and you ask yourself, what looks the most like this? And it's this. And then you compare. Did this release a hydrogen or did it gain a hydrogen when it became that? Lost a hydrogen. This hydrogen went away and you end up with that. So if this lost a hydrogen, what does that make this? The acid. And again, guys, once you know the acid, and it's not always first, but once you know the acid, everything falls into place. Because if this is the acid, what's that make water? The base. Now, guys, look, to do the conjugates, go to the acid, take away the hydrogen. Whatever's left is the conjugate opposite. So that makes this what? Conjugate base, and this is the conjugate acid. You get it? Is that okay? Now, guys, this is a term you need to write down. Guys, check this out. So this is an acid. It gave a hydrogen to water, and it formed H3O. This is an acid. It gave a hydrogen to water. It formed H3O. Now, guys, here's the trick. All acids do this. Anytime you have a substance that is an acid, it has to be in water. Guys, there's no such thing as an acid that is not in water. All acids have to be in water. And when an acid goes into water, it gives a hydrogen to water, and the hydrogen turns into H3O. And this is so important, we give H3O a name, and you need to write it down. It's called hydronium ion. Guys, hydronium ion is H3O plus ion. And hydronium ion is actually always formed when acids are added to water. And in order to be an acid, you have to be in water. So guys, when you get an acid burn, you are actually not being burned by the acid, you are being burned by hydronium ion. That's all that acids actually do, is go into water, release hydrogen, and form hydronium ion. So that's a term that you need to know. So guys, back to conjugate acids and bases. Let's do one more to make sure you're feeling comfortable. You okay to go on? Not yet? All right. How about now? So guys, let's do one more. Here's another equation. Ready? Let's do this. Don't write it down. Do it with me. So guys, here we have NH3. What looks the most like NH3 over here? NH4. So guys, look. Here we have NH3. Here we have NH4. So what did the NH3 do? Did it gain or lose a hydrogen? Gained a hydrogen. So what does that make NH3? A base. So I animated it backwards. So this is the base, which makes that the acid. You okay with that? So now, guys, let's do the conjugates. Go to the acid, take away a hydrogen, that makes OH. So what does that make OH? The conjugate base, and then the other is the conjugate acid. So guys, now we need to ask an interesting question. Which one is it? In these two examples, water was a base. In this example, water is an acid. So which one is it? Is water a base or is water an acid? Yes. And there's a name for that. It's called amphoteric. So guys, water is perfectly an acid and perfectly a base. The name for that is amphoteric. Guys, amphoteric refers to a substance that can act as a base or an acid depending on the other substance. So if you add an acid to water, water functions as a base. If you add a base to water, water functions as an acid. So the answer to your next question is yes. Are there other substances that are amphoteric? Lots, and you'll see some in homework. Yeah. Exactly. And actually, this is interesting, David. The technical definition of an acid is something that's more acidic than water. And the technical definition of a base is something that's more basic than water. And so because water is perfectly both, things that are acids are more acidic than water, and things that are bases are less acidic than water. Yep. So guys, how are we doing? Acids, bases, conjugates. Should we look at a couple more examples, understanding this is important? Let's try it. Here we go. So looking at these. Do you think maybe we could not write them down and just see how it goes? And guys, okay, I did actually animate these. So let's try this. So guys, over here we've got CH3, and over here we've got CH4. So I'm just going to write these in. That'll be easier. Waiting for my board. And there we go. So guys, here we've got CH3. Here we've got CH4. So what did CH3 do? Gained a hydrogen. So what does that make CH3? A base. So that then makes this the acid. Then how do we do the conjugates? Well, we go to the acid, take away a hydrogen. What's left is the conjugate base, and the other one's the conjugate acid. Is that okay? We okay with that? Do you want to try another one, or can we move forward? We okay? We're okay? Okay. So guys, understand that's all there is to the process. Take this, compare to this lost a hydrogen, that would make this the base, and then you just keep going. Wait, no, that would make this the acid. Gosh, I got all excited. That makes this the acid, so this is the base, conjugate, conjugate. Are we good? Okay. All right, so guys, we've got one more thing to do. Here we go. We're going to wrap up the day today by talking about pH. So guys, now given the conversations that we just had, we can finally now define pH accurately. We said earlier that pH measures hydrogen ion concentration, and that's not completely true. Guys, pH is actually a measure of the strength of an acid, focusing on the formation of hydronium ion. So pH is actually a measure of the strength of hydronium ion. And remember, hydronium ion is the ion that's formed when an acid goes into water. Because all acids have to be in water. And so you put the acid in water, the acid gives away hydrogen, the water picks it up, it forms hydronium ion, and then your conjugate base. So guys, technically, pH then is a measure of hydronium ion concentration. So guys, when you're done writing that down, you're not going to write anything else down that comes up on this slide. But I've got an interesting question that I want to explore with you. And by the way, guys, I made a mistake when I got us started. finishing writing this down, would you just take a second and reach down in your backpack or wherever and grab your calculators? You're going to need them. I forgot. No, so here's the trick. There's two kinds of acids. So guys, the question is, when we say that acids have to be in water, does that mean that acids just naturally form in water? And the answer is no. Acids are substances that are stable outside of water. They're molecules. And they are stable outside of water, but when you add them to water, they then function as acids. And there's actually two kinds. There are what are called strong acids and weak acids, and we're going to talk next week. But all of the strong acids, including battery acid and stomach acid and things like that, all of the strong acids are actually gases. You can buy them in tanks, and then you bubble it through water, and it reacts with the water, and it forms an acid. The other kind of acid, which are the weak acids, are actually crystalline substances. They look like sugar. And we've got bottles and bottles. So like vinegar is a weak acid. Vinegar outside of water is a crystal that looks like sugar. And then when you put it into water, it reacts with the water and turns into an acid. Yeah. You guys good? We okay? All right, so guys, don't write think. You ready? So here's what we know. We know that pH is a measure of hydronium ion, and you'll notice I underlined the word concentration. So guys, allow your attention to be drawn to that word concentration, and let's talk. Guys, what are our units for concentration? Molarity, right? Moles over liters. So guys, this is an interesting question. If pH is a measure of hydronium ion concentration, why don't we just use molarity? Makes sense, right? So guys, if we're talking about the concentration of hydronium ion, why do we use pH? Why don't we use molarity? Why use pH, and you're not writing this down, why use pH instead of molarity? And guys, there's a very interesting answer. Check out the logic. So here's the deal. Guys, even really, really strong acids, like these acids that I tell you, don't get them on you or you're gonna wish you were dead. Even really, really strong, nasty acids have relatively small concentrations of hydronium ion. Their molarities are relatively low. As a result, these small concentrations are easier to represent in scientific notation. So guys, imagine that we have an acid that has a molarity of 0.001 molar. You get that on you and you're going to be unhappy. But that number, 0.0001, is a pain in the butt to write, so it would actually be easier to just write this as 1 times 10 to the negative 4th. So guys, the reason that the thought then is that because these concentrations are so small, it's actually easier to write these numbers in scientific notation. Now here's the problem. Even writing these numbers in scientific notation, they're still a pain in the butt to write. So here's what we do. Imagine that we have an acid that has a hydronium ion concentration of 0.001 molar. That number is a pain in the butt. So let's make it easier. Let's put it in scientific notation. That number is still a pain in the butt to write down. Guys, this is why we use pH. Because guess what the pH of this acid is? 3. Do you see it? Guys, where did the 3 come from? It's right here. Guys, that's all pH is. pH is take the hydronium ion concentration, write it in scientific notation, grab the exponent from the number, and that's the pH. Guys, that's all pH is the concentration of hydronium ion written in scientific notation, and then we just focus on the exponent. That's why we use pH, because instead of writing this, or instead of writing this, we just got to write down 3. So guys, let me show you how this becomes easier. Let me give you an example of a pH scale, because it looks like this. So here we go, pH scale. So check out what you've got. Across the top, we've got hydronium ion concentrations, and across the bottom, we've got pH. So guys, let's go, let's go, stomach acid. So guys, right here is stomach acid, and stomach acid has a pH of 2. What does that mean? Well, that means the hydronium ion concentration is 1 times 10 to the negative second. Or if we go up here and we talk about, let's go, did you guys know this, Coke? Coke has a pH of 4. You guys know that if you get rust inside the radiator of your car, you can drain the antifreeze out of your radiator, fill it up with Coke, and it'll eat all the rust out of your radiator? It's scary stuff. So guys, Coke has a pH of about 4. So guys, what does that mean? Well, it means that its hydronium ion concentration is 10 to the negative 4th. Guys, that's all pH is find the concentration, and that's the pH. Did you guys know this? Blood. The pH of your blood is 7.4. Is that an acid or a base? It's a base. Your blood is slightly basic. So what does that mean? Well, that means that the concentration of your blood, the hydronium ion concentration of your blood, is 10 to the negative 7.4. So guys, if you know the pH, bring it up, and that's the hydronium ion concentration, the exponent times 10 to the negative. You get the idea? So, guys, look at what this does. What this does is it then creates a relationship between pH and hydronium ion. So pH 2, hydronium ion at 10 to the negative second. If we go down, I turned off my board. I can just click. So guys, if we go down here and if we go to pH 6, that would be a hydronium ion concentration of 10 to the negative 6th. But guys, look what happens when we write this out. When we write it out, it's actually this. It's 10. So 10 to the negative 6 is 0.00001. And that's why the higher the pH, the lower the acidity, because these are negative exponents. So if we're a pH of 2, this is 10 to the negative second, which is 0.01. If we're pH 6, that's 10 to the negative 6, which is 0.00001. So as the pHs get bigger, the concentrations get smaller because they're negative exponents. See the relationship? So guys, what are we going to do with this? Well, we are actually going to pull these ideas together mathematically. So it just keeps going. If we go to 10 to the negative 12th, it just keeps going. But guys, notice what we've done. We have now created a relationship between hydronium ion and pH. And this relationship, because it carries all the way through, we can write it as an equation. This is what I want to write down. Guys, as an equation, it looks like this. pH is equal to the negative log of hydronium ion concentration. So guys, what we need to do is we need to figure out how to solve this equation. So grab your calculators. We're going to solve one of each, and then we're done for today. So guys, it goes like this. I'm going to give you 2 examples of each type of solving process. So over here, and I forgot to mention, guys, these brackets right here are not parentheses. They're brackets. They actually mean concentration or molarity. Forgot to mention that. So So that is the molarity or the concentration of hydronium ion. So guys, let's do this. Don't write down the questions, but we will write down the solutions. Here we go. Question number 1 is this. What is the pH of a solution with a hydronium ion concentration of 1 times 10 to the negative 4th? What's the answer? Do you understand that it's 4? Yeah? Guys, 1 times 10 to the negative 4th, the pH is 4. But now guys, watch this. What if the concentration of hydronium ion is 3.6 times 10 to the negative 4th? What's the answer? It's not 4 anymore. Do you see it? Guys, why is the answer no longer 4? Because this is no longer a 1. When this is 1 times 10 to the negative 4th, the pH is 4. If this is not a 1, the answer is not 4, and now we need to solve it. Guys, do this with me. Write down your equation. pH is equal to the negative log of hydronium ion concentration. The brackets, not parentheses, guys. It's important. It's brackets. Now you're going to plug this number into your calculator. Well, into the equation and then your calculator. So now we plug in the hydronium ion concentration. pH is equal to the negative log of 3.6 times 10 to the negative 4th. And now, guys, we need to solve. Grab your calculators. If you have a TI graphing calculator, you can type this in exactly as it looks on the screen. But remember, your negative sign is your change symbol sign down here by the 0. So guys, plug this into your calculator. Negative, and then log, and then 3.6 times 10 to the negative 4th. Guys, plug this into your calculator, and you will know that you got it right when you get the answer 3.4. Now guys, if you cannot get your calculator to spit out the number 3.4, we are not going to spend the time right now to help you make peace with your calculator. I would love to do that at another time, but to sit down with you as individuals and go, how do you make my calculator work, is unfair to everybody else. So guys, you'll know that you've got this right when you get 3.4. If you're not getting 3.4, you know you need to figure out your calculator. Go ahead, Nate. Is that the problem? No, absolutely, because mathematically, these are parentheses, but in chemistry, the brackets mean the number that goes in there is molarity. So guys, what I'd like to do is I'd like to show you how to solve the other type of problem, and then we'll give you a little, we'll call it quits there. So guys, notice what we did. We were given the hydronium ion, we came up with pH. Now guys, we've got to go in the other direction. Given the pH, you've got to be able to come up with hydronium ion. So guys, you're not writing the questions, but read. What is the hydronium ion concentration of a solution with a pH of 8? What's the answer? 1 times 10 to the negative 8 molar, yes? Okay, but guys, what if this is not a whole number? What if it's something like this? What if the pH is 8.12? Well, now we need to solve, right? So guys, don't write this down, but just watch. So guys, what we've got to do is this. We need our equation, but now we are solving for hydronium ion given the pH. So guys, what we've got to do is we've got to take this equation and solve it for hydronium ion. Now, if you understand logarithmic rules, you could probably do this on your own, but if you can't, this is it. Write it down. Hydronium ion concentration is equal to 10 to the negative pH. Or, given our particular problem, hydronium ion is equal to 10 to the negative 8.12. And then guys, that's what you need to type into your calculator. So the second function of your log button, What does it say? Where's your log key? Yeah, so guys, the second function of your log button should be a 10 to the x. So go second function log, which is your 10 to the x key, then negative 8.12, and you'll know that you've got it right when you get 7.59 times 10 to the negative ninth. So guys, as you're working on getting that sorted out in your calculator, if you are not getting the right answers, you need to talk to me or somebody that can help you get your calculator to work. Guys, you already have your homework in your possession. This is me being real with you. Guys, this homework assignment is long and difficult. But remember the conversation that we had a couple days ago. Guys, every moment of investment that you spend now is going to save your butt at the end of May. So guys, this homework assignment fairly should probably be done over the course of 2 class periods or 2 days. Start on it tonight, finish it up Thursday night. We're turning it in on Friday. Guys, do yourself proud and walk in here Friday with this done. If you need help, please let me know. And then guys, Friday, actually we're getting back into a more normal rotation on Friday. It will then become lecture lab, lecture lab, lecture lab. So guys, today on Friday, we will cover new material. So guys, you've got your homework in front of you. Freddie, I know you need one. Please be patient. And look for test remediation next after spring break. And we'll see you Friday.